So, I'd like you guys to do a bit of practice. Can you please draw an energy diagram of both of these reactions, labeling the activation energies and the delta H? For your first reaction, it has a negative delta H, indicating that this is an exothermic process. Exothermic process meaning that more energy is released when the bonds are formed than had to be consumed to break the reactant bonds. So we have this negative delta H where energy is being released and the system has less energy at the end than it did at the beginning. Opposingly, the second reaction has a positive delta H, indicating that it's an endothermic process, meaning that more energy had to be put into the reaction to break the reactant bonds than was released when the product bonds formed. So we have a positive delta H value, and where delta H again is the difference between where we start and where we end between the reactants and the products. And activation energy is the leap from where you start up to the highest energetic point. Nice work, all. So now going back, okay, beautiful. Moving along, just to practice your Lewis structure drawing skills, I'm going to ask for you guys to draw the Lewis structures of all of these compounds. Now, don't want to confuse anyone, this isn't strictly related to kinetics, but kinetics does involve the actual steps of bond breaking and bond forming, so it's appropriate, but this is not something that you need to do in any kinetics problem. Per se. This is just a skill we need for the AP test, so I want to take this opportunity to build it up right now. So draw yourself some Lewis structures. Here are the Lewis structures for the first reaction. Don't make fun of my drawing. This was the best I can do on this program. So you'll see the Lewis structures for the first reaction right here. Second reaction was a little bit more complex in terms of Lewis structures. We have, so NO and NO2 both involve single electrons instead of lone pairs on the nitrogen atoms. This was the only, well, it was the best structure you could draw given the amount of electrons you had. For both of these structures, you had an odd number of electrons. So you would know that you would necessarily have to have a single electron somewhere. And it's on the nitrogen instead of on the oxygen because oxygen is more electronegative than nitrogen. So if there is a struggle between electrons, oxygen is going to win out every time because it's more electronegative. It has a greater ability to attract electrons. Then we have carbon monoxide and carbon dioxide pictured here as well. And then also don't forget the resonance in NO2.